here's sine squared. Let's see if we can figure out some kind of trig identity that would give us another way of thinking about it. It does still look like a sine wave or cosine wave, right? It doesn't have sharp angles or anything. Would you say it looks more like a sine wave or a cosine wave? Well, it's kind of got a center line here at a half, and it doesn't start at the center line and go up like a sine wave would. It doesn't start at the top and move down like a cosine wave would. It starts at the bottom and moves up, so that sounds like a negative cosine. So if I just put negative cosine there, it has the right general idea, but what else can we say? How else do we need to adapt this negative cosine to match our sine squared? The amplitude of the sine squared is just from 0 to 1, so its amplitude is a half, where the cosine has a full amplitude of 1. So that's looking good. The sine squared seems to do a cycle twice as fast as the cosine here, so let's put in a frequency multiplier of 2. That's looking really good. And now we just need to shift it up so its center line is a half rather than 0. So we can do plus a half, and that looks really good. Let's give this a function a name. And now, how can we check that those two are actually the same, not just good by eye? Well, we could subtract them and hopefully divide them, and the ratio would be 1, hopefully. That looks like it's a constant of 1. Or we could subtract them, and we should get 0. That looks like it's basically 0. So that seems pretty reliable. You might actually remember this as one of the double angle or half angle identities, depending on how you learned it. So let's go back to paper and pencil. So we just saw in Desmos that sine squared is the same as cosine 2x with an amplitude of negative half, or upside down cosine with an amplitude of half, plus a half shift to the center line, which you could also write this way. We didn't prove that it's true. We gave some evidence, but it turns out it is true. So let's go back to the problem we were working on, finding the average value of the squared voltage over one full cycle. So pause the video and write down a formula for the average of that function. All right, welcome back. So to take the average of a function, we do 1 over b minus a integral a to b of f of x dx on some interval a to b, right? So let's specialize that to this function. We might as well start at time 0, and how far out do we want to go? Not 2 pi, that's for a plane sine wave, but for the voltage, the wavelength was 1 over 60 of a second. And the formula, the value of the function we're averaging is v squared. So we got 1 over 60 minus 0, integral 0 to 1 over 60 of v of t squared dt, and then rewrite that using the formula we know for v of t. So we have 1 over 60 minus 0, integral 0 to 1 over 60, 155 sine 2 pi times 60 times t squared dt. And then, how are we actually going to do that integral? We'll talk later about some of the other ideas we might have, but we're kind of thinking trig identities at this point, right? So let's apply a trig identity to the sine wave there. So we'll still have the same thing out front. The 155, we can just apply the squaring to that and then not worry about it as part of the trig identity. So instead of sine, I write cosine of 2 times whatever was in the sine. And I'll have this half out front, 1 minus cosine of 2 times whatever I was taking the sine of. Up there I was taking it of x, and then I had 2x. Here I'm taking the sine of 2 pi 60t, so I'll do 2 times 2 pi 60t, and that's good. So is this going to be easy or hard to integrate? What can we do? Pause the video and work out what this is going to be before you come back. So 1 over 60 minus 0. The 155 is a constant multiplier. I can just copy it. The 1/2 is just a constant multiplier. I can just copy it. The integral of 1 is what? Just t. The integral of cosine is sine. 2 times 2 pi times 60t. So at the same frequency. But then you have to divide by the frequency you're using. You could do a u substitution there if you wanted to, or you can just remember that shortcut. So 2 times 2 pi times 60. And we're doing all that from 0 to 1/60th. Okay, what can we do now? Basically just plug in the 1/60th and 0. We got 1 over 60 minus 0, 155 squared times 1/2. And then what do we have? 1 over 60 minus sine of 2 times 2 pi times 60 times 1 over 60. All divided by that stuff. Minus what you get when you plug in 0, which is 0 minus sine of, plug in 0 there, you get 0 over stuff. And does this simplify? I hope so. So 1 over 60 minus 0, 155 squared times 1/2. And then we have 1 over 60. And then what is this sine? The 60 cancels the 60, and I get sine of 2 times 2 pi. Sine of any even multiple of pi or any multiple of pi is 0. So I get minus 0 over 2 times 2 pi times 60 minus 0 minus 0. And that's just 0, and I'm left with a 1 over 60 here and a 1 over 60 out there. A 1 over 60 out there, so I can cancel those. I can only cancel those because these are zeros, and this is now just a multiplication rather than a multiplication with addition. So all together I get 155 squared times 1/2. Maybe I should explain this part better in writing. So this is sine of 2 times 2 pi times 1. Sine of any integer times pi is 0. All right, so overall, our average squared voltage is 155 squared over 2. So let's write that down. So what does that tell us? Well, we don't usually think in units of square voltage, right? Let's see what we can do to fix that. I almost said rectify, but that's an electrical joke. Let's talk about what the effective average voltage is. It would be whatever voltage produces a power, whatever constant voltage produces a power of 155 squared over 2 in this case. So what number, when you square it, squaring because of the whole power is related to the square voltage, gives you 155 squared over 2. Well, it must be the square root of that. Which is the square root of 1/2 times the square root of 155 squared, which is square root of 1/2 times 155, which is somewhere in the 119 to 120 volt region, which is what you might have heard of described as common household power in the US is 120 volts. Some people say 110. So let's think about what we did. So we're saying that if you had a constant voltage, not cyclically fluctuating, what constant voltage would you need to give you the same power as the cyclically fluctuating voltage with an amplitude of 155? You would need a constant voltage of 120 DC rather than AC. What we did is we squared the function, we squared the voltage function. Then we took the average. Then we took the square root. And what we computed is called the root mean squared voltage. Which is abbreviated RMS for hopefully obvious reasons. So it feels backwards. You don't take the root first, then take the mean, then square stuff. You square it, take the mean or average, and then take the square root of that. So RMS is a really useful concept in electrical engineering, obviously, but it's also related to other things. So it's related to root mean squared error, or RMSE, in statistics and machine learning and other things. And standard deviation, maybe I'll write that all out. It's okay if you've never seen the formula for standard deviation or don't remember it, but let me show it to you anyway. It's the square root of 1 over, and some people say minus 1, sum of xi minus x bar squared. So there, we're taking the mean of the data, subtracting it from each data point, that gives us a deviation or an error from the mean, squaring that, taking the mean of all that, like add stuff up, divide by the number of things, and then taking the square root of that. So it is a root mean square of something. I made a video about using root mean squared error when doing linear regression and stuff for another class. I'll put a link to that in the description.